we can use the derivative to find out if a function is increasing or decreasing on a given interval. In the interval a is less than or x is less than or equal to b, our function f of x is increasing if its derivative f dash of x is greater or equal to 0. And it's decreasing if f dash of x, its derivative, is less than or equal to 0 for all values of x in that interval. If we look at the graphs, the graph of y equals x cubed plus x is increasing for all values of x as its derivative, or the gradient, is positive, i.e. greater or equal to 0. The second graph, however, is only increasing on two sections. The first is between -1 and 0, and the second is x is greater than 1. It is decreasing on the other two sections of the graph, so here and here. And again, if we derive these functions, we would find that f dash of x is less than or equal to 0 when it's decreasing and greater than 0 when it's increasing. So if we have a look at this example, we're asked to show that the function is decreasing, which means that f dash of x is less than or equal to 0 for all values of x. So to do this, we need to firstly differentiate. So if we differentiate, we get f dash of x is equal to -3 minus 6x squared. So remember, to differentiate, we times by the power and take 1 off the power. If we look at this function, we know that x squared is always greater than or equal to 0. So that tells us that -6x squared must always be less than or equal to 0, which means that -3 minus 6x squared must also be less than or equal to 0. So f dash of x is less than or equal to 0 for all real values of x. The second example is slightly different. We're asked to find where the function f of x is increasing, which means that f dash of x is greater or equal to 0. So we need to find f dash of x. So to do this, we differentiate again. So times by the power and take 1 off gives us f dash of x is equal to 6x squared minus 6x. And we know that f dash of x is greater than 0 because it's increasing. So 6x squared minus 6x must be greater or equal to 0. And now we've got a quadratic inequality to solve. So for this, we need to factorise by taking out a common factor of 6x, which gives us 6x bracket x minus 1 is greater or equal to 0. So if we were just to write down the solutions to this equation equal in 0, we would get x equals 0 or x equals 1. And then we need to do a sketch because it's a quadratic inequality. So it crosses the x-axis at 1 and 0, the positive x squared. So our graph looks something like that. So that's 0 and that's 1. And then we need to identify the area that we want. We want the part where our graph 6x squared minus 6x is greater or equal to 0. So everything above the axis, x-axis. So we want these two sections of our graph. So now we need to write down two separate inequalities that give us these areas. So firstly, to get the right hand red part of our graph, we want all the x values bigger than 1. So x is greater than or equal to, because our question says equal to 1. And then we want all the parts of the graph that give us this left hand side. So x is less than or equal to 0. When we differentiate, we get the rate at which the function is changing. We also call this our gradient function, so differentiating gives us our gradient. But if we differentiate our gradient function, so if we differentiate again, we get the rate of change of the gradient function. This is also called the second order derivative, which we denote f double dash of x, or d squared y over dx squared. So starting off with the function y equals f of x, we can differentiate and get dy over dx equals f dash of x, or d squared y over dx squared, which is the same as f double dash of x. The rule for differentiating is the same, so if we take an example, y equals 5x cubed, and differentiate that, we times by the power and take one off, so we get dy over dx is 15x squared. We know that this is our gradient function, or the rate of change of our original function with respect to x. We can then do exactly the same thing and times by the power and take one off to get our second derivative, d squared y over dx squared equals 30x. This is the rate of change of our gradient function, or the second order derivative. So if we have a look at this example, we're given a function and we're asked to find the second order derivative, d squared y over dx squared. So firstly, we need to differentiate once, but to do that we need to rearrange the way this equation is written, as we cannot differentiate 2 over x cubed. So we need to rewrite this as y equals 3x squared plus 5x to the power of 10, and then using our indices laws we can write the last term as 2x to the power of minus 3. So because the x cubed is on the bottom, we can bring it to the top, but the power changes to a negative. We can now differentiate each of those terms, so we'll find dy over dx. So dy over dx is equal to, and we're just going to times by the power and take one off. So 6x plus 50x to the power of 9 plus 6x to the power of minus 4. And then to find d squared y over dx squared, we just differentiate again. So d squared y over dx squared is equal to 6 plus 450x to the power of 8 minus 24x to the power of minus 5. So this time we're asked to find the rate of change of the gradient function. So firstly we need to find the gradient function, f dash of x, and then differentiate again to find the rate at which this is changing, giving us f double dash of x. Again, before we can do that, we need to write our function in a form that we can differentiate. So that gives us f of x is equal to, again we can use the fact that we can bring the power from the bottom and write it on the top with a negative power, but the cube root is the same as a power of a third, so that overall gives us minus 1/3 plus 4 root x is the same as x to the power of a half minus 16x. So now we've written our equation in a form we can differentiate. We will differentiate to give us our gradient function f dash of x. So times by the power and take 1 off. So we get minus 1x to the minus 4 over 3 plus 2x to the minus a half minus 16. Well, now we've got our gradient function. If we differentiate it once more, we get the rate of change of the gradient function. So f double dash of x is equal to 4 over 3 x to the minus 7 over 3 minus 1x, or x to the minus 3 over 2, and our 16 differentiates to 0. Be careful when you are taking 1 away from your powers, and if you're not happy with this, use your calculator. Now, complete the following questions from the textbook exercises 12G on page 271 and 12H on page 272. Do the questions shown, so questions 1, 2, 3 and 4 from each exercise. Make sure that if you need help you come and see one of the maths teachers.